Thompson's experiment. We create a uniform magnetic field using an electromagnet perpendicular to the electric field applied by the metal plates. The field of the magnet flows from North Pole to South Pole. Now let's apply Fleming's left-hand rule. Let us stretch the 3 fingers of your left hand perpendicular to each other. If the index finger points to the direction of the magnetic field, and if the middle finger points to the direction of the electric current, you must be wondering why it is pointing in the opposite direction to the beam. That's because the beam is made up of electrons. The flow of current is usually in the opposite direction to the flow of the electrons. Then the thumb would point to the direction of the motion or thrust. So going by the direction of the thumb, the beam would actually move upwards. The displacement would be proportional to the magnitude of the magnetic field. If we increase the magnetic field, the beam will move further up. We adjust the magnetic field just so much that the beam moves up to hit the point P again on the flat surface. So we are just canceling the effect of electrical field by using the magnetic field. So force on the electron due to the electrical field is equal to the force on the electron due to the magnetic field.
Canal rays. Let us look at Goldstein's experiment setup. Goldstein used a discharge tube like that of Thompson, with an anode and a perforated cathode in the middle. He also used a fluorescent screen at the other end to sense the rays. At the pressure of about 1 millimeter mercury, there were cathode rays from the cathode towards the anode. Behind the cathode, we also observed a luminous stream of particles proceeding in the opposite direction of cathode rays. Goldstein called them canal rays as they passed through canal-like holes and came out on the other side.
Cathode rays are produced in a discharge tube. A vacuum pump is used to evacuate the discharge tube. The cathode of the tube is connected to the negative terminal of the battery, and the anode of the tube is connected to the positive terminal of the battery. It was observed that, at normal pressure, the gas did not allow the current to pass through it. However, when the pressure of the tube was reduced to 0.001 mm Hg, and a high potential difference between 10 kV and 20 kV was applied, at the end of the tube, a glow was seen on the walls of glass tube. The rays emitted by the cathode travel towards anode. The attraction of rays towards anode reveals that the rays carry negative charge. Properties of cathode rays are: 1. When any object is placed in the path of the cathode rays, these rays cast shadows. This shows that cathode rays travel in straight line. 2. When a wheel was placed in the path of cathode rays, the wheel rotates. This shows that rays consist of some particle and some kinetic energy. 3. In the presence of an electric field, the rays are deflected towards the positive plate. This confirms that cathode rays consist of negatively charged particles. 4. In the presence of a magnetic field, the rays are deflected. This shows that the cathode rays are affected by the magnetic field.
First regarding atomic models. After discovery of electron, proton, first model was proposed by J.J. Thomson. అంటే అప్పుడు ఇంకా న్యూట్రాన్ డిస్కవరీ అవ్వలేదు, రైట్? ప్రోటాన్, ఎలక్ట్రాన్ మాత్రమే. సో ఫస్ట్ మోడల్ వాజ్ గివెన్ బై J.J. Thomson. ఇట్ ఈస్ ఫేమస్ యాజ్ J.J. Thomson's plum putty model or apple pie model. Plum putty model or apple pie model. లేదా దాన్ని ఏమని చూస్తాం? వాటర్ మిలాన్ మోడల్. ఏంటి మోడల్ ఏంటంటే, if atom is assumed to be a sphere, total volume of atom is filled with a sea of positive charge. Right? This is field of positive charge. In this field, negatively charged particles, that means nothing but electrons. Electrons are embedded in this field. Right? So, electrons are embedded in a sea of positive charge, whether in a field of positive charge. This is the model proposed by J.J. Thompson. Next, another scientist by name Rutherford. Rutherford is nothing but a student of Thompson. He want to verify whether the model proposed by Thompson is correct or not. Right? So he conducted an experiment, and that experiment is famous as
Rutherford planetary.
Rutherford's Geiger Mersden experiment. Rutherford is a supervisor to that. So this experiment is famous as Rutherford's gold foil experiment. Rutherford's gold foil experiment or alpha ray scattering experiment. Gold foil experiment or alpha ray scattering experiment. What is alpha? Alpha alpha particles are discovered by Rutherford. Alpha is nothing but helium nucleus. Helium nucleus is called alpha particle. So alpha ray scattering experiment leda Rutherford gold foil experiment. So this is nothing but a thin gold foil. You can say thin gold foil. This gold foil is surrounded by phosphorescent screen or assumed as fluorescent screen, or we may call that zinc sulfide screen. Surrounded by phosphorescent screen such as zinc sulfide. And from a source of alpha particle, that means we will consider this is a lead chamber which is filled with radioactive material. This is lead chamber, and we will take some radioactive material here. The radioactive material continuously emit alpha particles. Those alpha particles are allowed to incident on the surface of gold foil. Right? This is radioactive material. So when this is done, alpha rays emitted from the surface of this radioactive material tries to hit the metal plate. This tries to hit the metal plate. Right? If Thompson's model is correct, according to Thompson, total atom is filled with positive charge. That means total atom surface is made up of positive charge. If this is correct, what is the charge of alpha particle? Positive charge. Atom charge is positive. Alpha particle is also positive. That means all alpha particles should bounce back. ఆటమ్ మొత్తం ఫిల్ అయ్యింది పాజిటివ్ చార్జ్, లోపల ఎక్కడో ఎలక్ట్రాన్స్ నిండిపోయి ఉన్నాయి, అంటే ఆటమ్ సర్ఫేస్ మీద ఏమన్నట్టు పాజిటివ్ చార్జ్ అయి ఉంది, మరి ఇది కూడా పాజిటివ్ చార్జ్ అయ్యింది. సో దిస్ పాజిటివ్ చార్జెస్ species must be repelled by atoms if Thompson's model is correct. But what he observed is most of the alpha particles are positive. ఎక్కువ alpha particles pass అయిపోయాయి. Few alpha particles are scattered at certain angles.
1 in 20,000.
Right? Few alpha particles are scattered at certain angles, and very few particles are bounced back.
Reflected.
Very few alpha particles are bounced back. So what he has observed? One, most of the alpha particles pass through. So as most of the alpha particles, అన్ని alpha particles వెళ్ళిపోతున్నాయి అంటే అర్థం ఏంటి? Atom must be empty, right? So most of the alpha particles are passed through. That means most part of atom is empty. ఖాళీగా ఉంది అని. Second observation, few alpha particles are scattered through certain angles. Few alpha particles are scattered with certain angles. అంటే యాక్చువల్గా ఆల్ఫా పార్టికల్ ఇలా వెళ్ళాల్సింది, ఇలా వెళ్ళింది, అంటే ఈ మధ్యలో యాంగిల్ చేసింది కదా, దట్ యాంగిల్ ఇస్ నేమ్డ్ యాజ్ స్కాటరింగ్ యాంగిల్ తీటా. దాన్ని ఏమన్నాం? స్కాటరింగ్ యాంగిల్ తీటా అని వచ్చింది. అర్థమవుతుంది? ఫ్రమ్ హియర్ దే మేడ్ ఏ కంక్లూజన్. కొన్ని ఆల్ఫా పార్టికల్స్ స్టార్ట్ అవుతున్నాయి, అన్నీ కావట్లేదు, కొన్ని స్టార్ట్ అవుతున్నాయి అంటే అర్థం ఏంటి? దేర్ మస్ట్ బి సంథింగ్ విచ్ ఇస్ రిపలింగ్ ఆల్ఫా పార్టికల్. మరి ఆల్ఫా పార్టికల్ ఇస్ పాజిటివ్ చార్జ్, దాన్ని రిపల్ చేసి ఎవరై ఉండాలి? పాజిటివ్ చార్జ్, అప్పుడే కదా రిపల్ అయ్యాయి. సో దాన్ని బట్టి ఏం చెప్పాడు? దట్ ఈస్ టోటల్ పాజిటివ్ చార్జ్ ఆఫ్ an atom is
Concentrated
in a small volume at its center, is concentrated in a small volume at its center. Right. ఇంకొక అబ్జర్వేషన్ ఏం చేశాడు? 1 in 20,000 particles. 1 in 20,000 particles bounced back. 1 in 20,000 particles bounced back. 20,000 particles పంపిస్తే ఒక పార్టికల్ వెనక్కి వచ్చింది. ఆల్ఫా పార్టికల్ వెనక్కి వచ్చింది అంటే అర్థం ఏంటో? టోటల్ పాజిటివ్ చార్జ్ మీన్స్ టోటల్ ప్రోటాన్స్. ఆల్ఫా పార్టికల్ మాస్ ఇస్ 4 times that of proton. ఆల్ఫా పార్టికల్ బరువు ఉంటే 4, ప్రోటాన్ 1. సో మాస్ ఆఫ్ ఆల్ఫా పార్టికల్ ఇస్ ఫార్ హెవియర్ దాన్ 4 times heavier than proton. మరి అలాంటి బరువైన పార్టికల్ వెనక్కి వచ్చేసిందంటే అర్థం ఏంటి? దేర్ మస్ట్ బి సంథింగ్ విచ్ ఇస్ ఫార్ హెవియర్ దాన్ దిస్ ఆల్ఫా పార్టికల్, రైట్? సో ఫ్రమ్ దేర్ హి మేడ్ ఏ కంక్లూజన్ దట్ ఈస్ టోటల్ మాస్ ఆఫ్ an atom is concentrated at its center. Total mass of an atom is concentrated at its center. And he named it as nucleus. So these are the observations and conclusions from Rutherfords experiment. So దీన్ని బేస్ చేసుకొని చూడండి. For example, this is atom. If I consider this as atom, right? So what is happened? Most of the alpha particles are passed through. ఎక్కువ alpha particles వెళ్ళిపోతున్నాయంటే అర్థం ఏంటి? They are moving away from nucleus. ఇలా వెళ్ళిపోతే ఇట్లా పాస్ అయిపోతాయి. If alpha particles are coming close to the nucleus, then they will be scattered. ఇలా దగ్గరికి వస్తే scattered. ఇంకా దగ్గరికి వస్తే ఇంకా ఎక్కువ స్కాటర్ అవుతాయి. అలా ఇంత దగ్గరికి వస్తే వెనక్కి వచ్చేస్తాయి. అంతేనా? బౌన్స్ బ్యాక్. అదే కదా జరిగేది. సో మోస్ట్ ఆఫ్ ద ఆల్ఫా పార్టికల్స్ ఆర్ పాస్ త్రూ, దట్ మీన్స్ మోస్ట్ పార్ట్ ఆఫ్ ఆటమ్ ఈస్ ఎంప్టీ. ఫ్యూ ఆల్ఫా పార్టికల్స్ ఆర్ స్కాటర్డ్ విత్ సర్టెన్ యాంగిల్. కొన్ని పార్టికల్స్ స్కాటర్ అవుతున్నాయి అంటే అర్థం ఏంటి? టోటల్ పాజిటివ్ చార్జ్ ఇస్ కాన్సంట్రేటెడ్ ఇన్ ఎ స్మాల్ వాల్యూమ్. అండ్ 1 in 20,000 particles bounce back. ఒక్క పార్టికల్ 20,000 పార్టికల్ పంపిస్తే 1 particle bounce back means alpha particle is bounced back means that possess very high mass compared to alpha particle. So దాని బట్టి ఏం చెప్పాడు? Total mass of atom is concentrated at its center called nucleus. So this is nucleus, right? And this is atom. And what is the charge of nucleus? Positive, because total positive charge is present at its center, right? This is what Rutherfords experiment is. Next, based upon this experiment, we need to calculate the distance of closest surface. That means when alpha particle is allowed to hit the surface of nucleus, మరి ఆల్ఫా పార్టికల్ వెళ్ళి కొంత దూరం వెళ్ళి వెనక్కి వచ్చేసింది కదా, ఎంత దగ్గరగా వెళ్తుందో మెజర్ చేస్తాం. We call that as a distance of closest approach, right? Let me stop here.
Rutherfords model of an atom. Rutherfords scattering experiment. In 1911, Rutherford performed an experiment in which he bombarded a thin foil of a heavy metal like gold with a team of fast-moving alpha particles, which are doubly ionized helium ions, He2+, each having 2 units of positive charge and 4 units of mass, 4U. These were obtained from radium placed in the cavity of block of lead and made into fine beam with a slit. He observed the scattering of the rays after hitting the foil by placing a circular zinc sulfide screen around the metal foil. Wherever alpha particles struck the screen, a flash of light is produced at that point on the screen. That the heavy body present in an atom must be occupying a very small volume. From these experiments, Rutherford made the following observations. Most of the particles, that is 99.9%, passed through the foil without undergoing any deflection. Some particles were deflected through small angles, and a few were deflected through large angles. Very few, only 1 in 12,000, were deflected back, that is, through an angle greater than 90 degrees. From these observations, Rutherford drew the following conclusions. Since most of the alpha particles passed through the foil without undergoing any deflections, there must be sufficient empty space within the atom. This small, heavy, positively charged body present within the atom was called nucleus. Rutherford's nuclear model of an atom. On the basis of scattering experiments, Rutherford put forward a model of atom known as Rutherford's nuclear model. There is a positively charged center in an atom called the nucleus, in which all the mass of an atom resides. The size of nucleus is very small as compared to the size of an atom. The electrons revolve around the nucleus in well-defined orbits. As some of the alpha particles were deflected by small angles, and since alpha particles are positively charged, they could be deflected only by some other positively charged body present within the atom. The alpha particles which deflected through small angles were those which passed far from this positive body. The alpha particles which deflected through large angles were those which passed close to the positive body. Since some alpha particles were deflected back, alpha particles are heavy particles. They could be deflected back only when they strike heavily inside the atom. Since number of alpha particles deflected back is very, very small, which shows that the positive charge and mass of gold atom must be occupying a very, very small volume. Drawback of Rutherfords model of an atom. According to Rutherfords model, an atom consists of a small, heavy, positively charged nucleus in the center, and the electrons were revolving around it. Whenever a charged particle, like electron, is revolving around a central force like that of nucleus, it loses energy continuously in the form of radiations. Thus, the orbit of the revolving electron will keep on becoming smaller and smaller, following a spiral path, and ultimately, the electron should fall into the nucleus, which means the atom should collapse. But this actually does not happen, and the atom is quite stable.